PCl5. P has got 5 electrons in its valence shell. Chalo, P 1, 2, 3, 4, 5. Just draw 5 electrons, simple. Okay, and how many chlorines are there? 5 chlorines are there. Each of them has got how many electrons? Each of them has got 7 electrons in its valence shell, right? So draw 5 chlorines. 1, 2, 3, 4, 5, 6, 7. Again another one. 1, 2, 3, 4, 5, 6, 7, and so on. So these chlorines, each chlorines can have 8 electrons undoubtedly. But how many electrons will the phosphorus have? Its own 5 electrons, and 5 chlorines, 1 electron, that is 5 electrons. Total how many electrons it will have? Total 10 electrons it will have, right? Yes or not? Total it will have 10 electrons. So Cl, this is also 1, 2, 3, 4, 5, 6 and 7. Another Cl, 1, 2, 3, 4, 5, 6, 7. Okay, this Cl is also becoming 8, this Cl is also becoming 8, and another Cl, 1, 2, 3, 4, 5, 6 and 7. This is also becoming 8. Clear? But what about phosphorus? What about phosphorus? The phosphorus is becoming 10, right? Okay, because everywhere a pair of electron is there common. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is also not octet, but it is more than octet. It is more than octet. If you do it for SF6, you can try it. If you do it for SF6, there will be 12 electrons in sulfur. Because sulfur has got 6 electrons, each fluorine will give 1 electron, so there will be total 12 electrons in the sulfur atom. Okay, that means that is exceeding the octet. But still, once again I am saying the compounds are very much stable. The compounds are very much stable. Since they are very much stable, they cannot be explained by the Lewis dot model. Okay, that is another limitation of Lewis dot model, and that is called, that's the second one, that is called expanded octet. We call it expanded octet. Okay, so octet was the theory was octet, that it has to be 8. Certain compounds are there which is having less in number than 8, those are called incomplete octet, and certain compounds, certain stable compounds are there which has got more than 8, which are called expanded octet. Now I don't know how some of you told that you had done for, I will come back now to this. Some of you had told me that you had done it for NO2. I don't know how did you do the Lewis dot model or Lewis dot structure for NO2. It's very surprising to me because it cannot be done. Why it cannot be done, Why it cannot be done, The number of electrons in nitrogen, obviously valential electrons in nitrogen is 5, right? The number of valential electrons in nitrogen is 5. Number of valential electrons in each oxygen is 6. So 2 oxygens, there will be 12. There will be 12. So total number of valential electrons in this molecule is 17. That's an odd number. That's an odd number. 17 is an odd number. Now can you make it octet or doublet with the odd number? Certainly not. There will be always an extra electron that will remain. Okay. So if any molecule contains odd number of electrons in its valence shell, any molecule, the total number of electrons in its valence shell is odd, we cannot explain the structure of it simply by the Lewis dot model. That's the third limitation. For example, suppose another example I am giving. Suppose if I tell you to draw NO, that is nitrogen monoxide, right? Okay, we know that nitrogen monoxide exists. Okay, but this nitrogen monoxide, can this be explained by Lewis dot model? Let us see that. Nitrogen has got 5 electrons in its valence shell. Oxygen has got 6 electrons in its valence shell. So the total number of electrons is 11. And 11 electron system or any odd number electron system simply cannot be explained by the Lewis dot structure because it demands doublet or octet, that means even numbers. Okay, so any compound having the total number of valence electrons odd cannot be explained by the Lewis dot model. and these are the limitation of Lewis dot model. Okay, these are the simple limitation of Lewis dot model. Okay, 3 limitations. Hence we have to move forward. That means how can we overcome this limitation? How these limitations can be overcome, and hence comes the next theory, which we are going to start, certainly going to start today. Okay, I mean the theory to certainly we are going to do, but the completion of this we are going to do it in the next class. But again and again I am saying that I am giving you some homework. Please do that. Otherwise you are not going to be able to do the questions. I am repeatedly saying, until and unless you are not practicing, it's not going to help you out. Okay. The next theory which actually tried to overcome the limitations of the Lewis dot model is called valence shell electron. From the word itself you can understand this, electron pair repulsion theory. Valence shell electron pair repulsion theory. Okay, in short we call them as VSEPR theory. Okay, valence shell electron pair repulsion theory. Okay, now what does this theory say? First we must understand the theory, then only we have to apply it. First please understand the theory. Suppose I am just taking one particular example I am taking, and with that example I am saying, then obviously we are going to do a lot. Okay, suppose I am taking a simple one, BCl2. Fine. Okay, all of you know what is the Lewis dot structure of BCl2. Let me draw it. Lewis dot structure of BCl2. B has got 2 valence electrons. Cl has got 1, 2, 3, 4, 5, 6 and 7. Another Cl has got 1, 2, 3, 4, 5, 6 and 7. So Cl will have 8 electrons, this Cl will have 8 electrons, but beryllium will have how many electrons? 4 electrons, right? 2 pairs of electrons. Now, valence shell. Whose valence shell? First question, this theory, I am going to the theory. Whose valence shell? Valence shell of the central atom. In BCl2, what is the central atom? The central atom is beryllium. Okay, suppose if I talk about methane, CH4, the central atom is carbon. If I talk about PCl5, whichever we had done, PCl5, the central atom is P. Okay, so whose central atom, whose valence shell? First of all, the valence shell is of the central atom. It's the central atom's valence shell. First point. Electron pair. Obviously, central atom will have the electron pair in it. There can be 2 types of electron pair that we had studied last day only. One can be bond pair. That particular pair is involved in the formation of the bond. And another type of pair that is present is lone pair, which does not have anything to be done, the lone pairs of electrons, okay, which are not taking part in the bond formation. Fine. So valence shell electron pair, you understood this. Repulsion theory. What is this now? See, in this theory, the valence shell of the central atom is considered as a sphere. The valence shell of the central atom, please understand it. Valence shell of the central atom is considered as a sphere. Okay, just it is considered as a sphere. If it is considered as a sphere and the electrons present in it, or the electron pairs present in it, they are present as a pair. The electron pairs present in it are at the surface of the central atom. Okay, it might be the bonded pair, it might be the lone pair of electrons. Just think of a ball, a football, okay, and on the surface of the football, the electron pairs are there. Okay, that football is what? It's nothing but the valence shell of the central atom. This theory says this is the valence shell of the central atom simply, and the electrons of that central atom are present on the at the surface of the what? At the surface of the ball, or at the surface of the shell of the sphere. Okay, fine. Now, according to this theory, these electron pairs will place themselves in such a way on the surface. They will place themselves in such a way on the surface so that they experience the minimum repulsive force. Means what? Obviously these electron pairs will repel each other. That चाहे वो lone pair हो, bond pair हो, कुछ भी हो, they are going to repel each other. Okay, but the repulsion should be minimum. And when the repulsion is minimum, when they are farthest distance away from each other, they are on the surface only. But where they should be, suppose we are talking of this beryllium. Beryllium is considered as at the center of the ball. Just imagine this, a ball is there at the center of the ball, the beryllium is there, and this beryllium has got two pairs of electron. Now where should these two pairs of electron be placed on the surface of the sphere so that they experience the minimum repulsive force? Just think of a diameter. Think of a diameter in the surface, in the sphere, okay, of the sphere. Just think any diameter of the sphere. If two electrons are placed in the two sides of the diameter, then only the force of repulsion will be minimum. If anyone is moving anywhere, the force of repulsion will be more. Yes? So, according to this theory, the pairs of electrons, whether it is bond pair or lone pair, they will be placed themselves, on the surface in such a way so that the force of repulsion is minimum. Okay, that's the first point. What did I say? That the valence shell of the central atom is considered as a sphere, and the electron pairs present in the valence shell of the central atom are on the surface of the sphere. The electron pairs will be placing themselves in such a way so that they obtain or they experience the minimum repulsive force. Okay, and repulsive force can be of three types. The repulsive force can be between bond pair and bond pair. The repulsive force can be between bond pair and lone pair, and the repulsive force can be between lone pair and lone pair. Bond pair are the ones which are taking part in the bond formation. Lone pairs does not have anything to do. इसका कोई काम नहीं है लोन पेयर का, उसीलिए लोन पेयर और लोन पेयर का जब रिपल्सन होगा, दैट रिपल्सन इज मैक्सिमम, और बॉन्ड पेयर का जब रिपल्सन होगा वो रिपल्सन मिनिमम है. So these three repulsions are in the order of lone pair is greater than lone pair, bond pair is greater than bond pair. That's the next point. One more point is there, but you are going to join with the same ID password because the time is up. Okay, so I'm just ending it and then you join again with the same ID password.